So welcome to the final part. We're going to continue our discussion of axioms, results that we can deduce from the axioms of our vector space. So let me make myself disappear. Okay, so I left this little theorem here, and hopefully you had some time to think about it. And so what we're saying is if I take a scalar multiplied by a vector v, I get the zero vector. Okay, and so we're going to prove this now. So I actually started it. So we have that 0 times a vector v is equal to 0 plus 0 times v, because we're just looking at the same constant right over here on both sides. And here we're using the distributive property. Okay, so we're multiplying out. Okay, so this holds by the axioms. Okay, now 0 times v is a vector. Okay, so it has an additive inverse. So what we're going to do is we're going to add the additive inverse of this vector to both sides. Okay, so we're going to add it to both sides. So on the left-hand side, I have 0 times v plus the additive inverse of my vector, and that should be equal to 0 times v plus 0 times v plus minus 0 times v. Okay, and now on this side, on the left-hand side, we have 0 because we have a vector and we subtracted its additive inverse. So this is the 0 vector on this side. And we can regroup things on this side. So 0 times v plus negative 0 times v. And this is becomes 0, so I end up with 0 times v. And there we go. We get the answer that we're looking for. We have that the 0 vector is equal to the 0 times the vector v. Okay, so this is another example of a property of a vector every vector space will have, and we can deduce it from the axioms. Okay, another example of this type of result is the following, is that here we have, in both cases, we have the 0 vector. Okay, so this is true for both of these, and it's saying if you take the 0 vector and you multiply it by a scalar, regardless of which vector space you're looking at, you're always ending up with the 0 vector. And the proofs kind of look the same, right? So in this case here, we have that lambda times 0 is the same thing as lambda times the vector 0 added to itself, right? 0 added to itself in terms of vectors is the 0 vector. And now we use our distributive property, right? So lambda times 0 plus lambda times 0. And now what we do is we add the additive inverse of this vector to both sides, right? And maybe I'll actually do that. We have lambda times 0 plus negative, its additive inverse is the same thing as lambda times 0 plus lambda times 0 plus its additive inverse. And then this simplifies to 0 on the left-hand side, the 0 vector, and on the right-hand side, it simplifies to lambda times the vector 0. Okay, so the result is proved. So that gives you another example of a property that we can derive from the axioms. And one more, actually a couple more for today. The first one, the next one here is saying something that's also very interesting, is that if we take a vector v and we multiply it by the scalar multiple, so this is the scalar minus 1, on the other side we're getting the additive inverse of the vector v. Okay, so notice how the different symbols mean different things on the two sides. So it's saying if I take a vector and I multiply it by the scalar negative 1, my answer will be the same thing as the additive inverse of that vector. Okay, now we have that we can write the 0 vector as 0 times v. Okay, so this was proved above. And 0 is the same thing as 1 plus negative 1, right? So I can replace 0, the scalar 0, with this scalar, And then I have my distributive property right here. So this tells me, so minus 1 times V is an additive inverse of V, right? Because I have V plus this vector gives me 0. But additive inverses are unique. But since inverses are unique, this means that this inverse has to be actually to the inverse of minus V, because they're both doing the same job. They're both playing the role as the additive inverse of V. Okay, so that gives you another useful property about vector space. Okay, and now you should be starting, if you read the textbook and tried some of these examples, you should be able to answer a question like this, which is saying, well, suppose that we have a constant and it's non-zero, and it has the property that C times V is equal to 0. So this constant isn't 0. When you multiply, you get the 0 vector. What can you say? Well, the problem is saying that this vector that you started with should have been the 0 vector. Okay, and let me show you how this works, how you would prove this. Well, since C does not equal to 0, C inverse, which is 1 over C, is inside of F, right? So we have our constants are coming from the real numbers or the complex numbers, so 1 over C exists. So 1 over C times V is equal to 1 over C times the vector 0, right? So that because we're given that C times V equals 1, right? And now this is equal to 0. Okay, so let's put now some of the pieces together. So now 0, which is equal to 1 times C times the 0 vector, is equal to 1 times C times V. And then here I have a scalar, and here I have a scalar, so I could regroup it. So I have 1 times C times V. This is one of the properties of the axiom. And inside here is just a constant, right? So that's 1 times V. And then by one of the axioms of the vector space, this is just equal to the vector V, right? So I have that 0 is now equal to the vector V. So in the second lecture, okay, we've covered actually a fair number of things. So here's the key ideas you should take away from today's lecture. And let me move this over for a minute. Oh, let's see. Okay, move this a little bit. Okay. So some of the key ideas here are, what is the definition of a vector space? This is something you should internalize and get used to. Have a good collection of examples that you can think of when you're doing these vector spaces. So when you're trying to do things more generally, it's sometimes easier to kind of figure out what happens in special cases and then extract. And then you should also know some of the basic properties of vector spaces, like the ones that we proved here. So that's it for lecture 2. In lecture 3, we'll carry on. The topic for lecture 3 is subspaces. Okay, have a great day.